Okay, let's start our lesson like this, members. In this lesson, we're going to record the determination of distribution coefficient. We already know what distribution coefficient is. And in my class, I have one student. It is an online class, but I have got one student in my class so that we go through this lesson together. And we are going to be looking at the determination. We are going to look at the determination of distribution coefficient of a solute, distribution coefficient of a solute between two immiscible solvents, in contact. Distribution coefficient. We already know what distribution coefficient is, Kd. That constant ratio of molar concentration of a solute in a certain solvent to the concentration of that very solvent in another, we are looking at the constant ratio of a certain solute in a given solvent to the concentration of the very same solute in another solvent at a constant temperature. But now we want to look at how do we determine Kd, or the partition coefficient, experimentally. Now, in this case, you need to know that we get a known mass of a solute and dissolve it in known volumes of two immiscible solvents. You need to understand what the limitation is, because these limitations are going to be guiding us throughout. The first limitation, if I'm to remind you, we said that the first limitation is that the temperature of the mixture should be kept constant. That is 1. 2, we say that the solute should be soluble in both solvents. 3, we said that the solute must not react with either solvents. 4, we said that the solute should not circulate either solvent. And 5, we said that the solute must not dissociate or associate in either solvent. That is to say, it should remain in the same molecular state in both solvents. Now, after having gotten all those limitations, now we come to the real chemistry of determination of the distribution coefficient of a solute between two immiscible solvents in contact. When you get a known mass of a solute and you dissolve it in known volumes of two immiscible solvents in contact in a separating funnel. Why do we use a separating funnel? A separating funnel is the set of apparatus that can help us separate immiscible liquids. And why? How does it separate them? The moment you mix them together into that separating funnel, they are going to form a junction, or they are going to form two different layers separated by a certain junction that we call a liquid junction. So you are going to get those two immiscible liquids, you put them into a separating funnel. Okay. Now the mixture of those two liquids is shaken so that that solute that has been added to those solvents can dissolve in both. What am I trying to say? If I get my separating funnel, I'm assuming that this is my separating funnel. If I get my separating funnel, of course, it must have a tap on it, and there it must be. The moment you put solvents, these solvents are going to form different layers. They're going to form different layers. So if you add a solute, and you shake, you have to shake the mixture so that this solute added distributes itself between these two solvents. But remember, it won't react with them, neither will it dissociate in them. So what happens is that the moment the mixture is shaken until equilibrium is established, then these layers are separated, and the concentration of the solute in each layer can be determined by titration. So we are going to look at how we get the concentration of the solute in each layer by the method of titration. But you know, when we are carrying out titration, we have got what we call a standard solution in titration. And a standard solution is that solution whose concentration should be exactly known during the method of titration. Now, we choose that standard solution depending on the nature of the solute. These ones are solvents, well, but to choose the standard solution to use during the titration procedure, it depends on the nature of the solvent. That is to say, if the solute is acidic, if you have a solute which is acidic, your standard solution is an alkaline solution. If the solute is acidic, then the standard solution should be alkaline. And in that case, we opt to use like sodium hydroxide solution as a standard solution. Okay, sodium hydroxide solution. But if the solute is acidic, rather is alkaline, if the solute is alkaline, there we opt to use an acidic media, or we decide to use an acidic solution as our standard solution. So if the solute is alkaline, there we use an acidic solution as our standard solution. But if the solute is iodine, if the solute is iodine, here we strictly use standard sodium thiosulfate. We standardly use sodium thiosulfate as our standard solution. So the end point during titration is detected by the indicators that are selected depending on the titrant. Okay, we select an indicator depending on the titrant. That background is going to enable us describe how we can determine the partition coefficient of different solutes between given solvents. For example, determination, let's begin with determination of partition coefficient. One can call it distribution coefficient or distribution constant. Partition coefficient of butane dioic acid. Butane dioic acid. You can call it succinic acid or succinic acid between water and ether. Between water and ether. Determination of partition coefficient of butane dioic acid or succinic acid between water and ether. The procedure is you get a known mass of butane dioic acid and you add it to a known volume of water in a separating funnel, and then a known volume of ether is also added. Okay, then you have to shake the mixture when it is sealed and allow it to settle so that equilibrium is established at constant temperature. Then these layers are separated and the fixed volume of the aqueous layer is pipetted and titrated against the standard solution of sodium hydroxide. Why do we use sodium hydroxide as a standard solution? Because we are having our solute as an acid. If you have a solute as an acid, you have to use the alkaline solution like sodium hydroxide solution as your standard solution. And that one suitably, we can use also phenolphthalein indicator. Okay. Now, what we do, let me try outlining these steps very fast. Unknown mass of butane dioic acid, is added to a known volume of water in a separating funnel, and a known volume of ether also added. A known volume of ether also added. After adding a solute in water and ether in a separating funnel, you start shaking the mixture. The mixture is shaken. The mixture is shaken. Why shake it? Because we want equilibrium to be established between the solute and those solvents in which it is being dissolved. So the mixture is shaken and left sealed, comma, allowed to stand or allowed to settle such that equilibrium is established at constant temperature. So that equilibrium is established at constant temperature. Now, the layers, as it settles, the layers are going to be formed. And these layers, the liquid, rather the solute is going to distribute itself between those two layers. So we shall have the solute in the aqueous layer, which is the water layer, and the solute in the organic layer, which is the ether layer. Now, what happens is that the layers are separated. The layers are separated. The layers are separated and a fixed volume. And a fixed volume of the aqueous layer, that is the water layer, a fixed volume of the aqueous layer is pipetted and titrated against a standard solution of sodium hydroxide, standard solution of sodium hydroxide, using which indicator? Phenolphthalein, phenolphthalein indicator, using phenolphthalein indicator. Now here we shall have our butane dioic acid, C2H4, being dioic. It means we have carboxyl groups, two of them. Dioic acid, we have titrated it against sodium hydroxide, and we shall form C2H4 COO Na2 aqueous then plus 2 molecules of water. Yes, that's what we form. Now, since the sodium hydroxide is standard, it means that from the volume of the standard sodium hydroxide solution used, the concentration of butane dioic acid in the aqueous layer is determined. That is the step we put. From the volume of standard sodium hydroxide solution used, comma, the concentration of butane dioic acid in aqueous layer is determined. We have determined the concentration of butane dioic acid in aqueous layer. But we also need to get the concentration of butane dioic acid in the organic layer or the ether layer, and that is obtained by subtraction, because you'll be having the total mass or the total concentration of butane dioic acid. Okay, so if part of it went to the aqueous layer, then we can get the part of it that went to organic layer, by subtraction. So you're going to say that the concentration of the acid in the organic layer is then obtained by subtraction. And the last step, after having obtained the concentration of the acid in the aqueous layer and the organic layer, then now we can get our Kd. So the partition coefficient Kd, the partition coefficient Kd is obtained from the expression Kd is equals to concentration of butane dioic acid in the water layer or the aqueous layer over the concentration of butane dioic acid in the ether layer. The question of this nature can come and you find 5 marks or 6 marks on it. Describe an experiment to determine the partition coefficient of butane dioic acid between water and ether. What is mentioned first is what you make your numerator. Okay, so that is it. That is how we get the partition coefficient. To summarize the steps again, we say that you get a known mass of a solute, you add it, okay? You add it to a known volume of water in a separating funnel, and then you add another solvent. You will mix until equilibrium is established or until the solute has distributed itself in those solvents very well. After that total equilibrium having been attained, those layers are separated at fixed volume, separated, and then you pick a fixed volume of an aqueous layer, you titrate it against a standard solution of sodium hydroxide. We said that we have used sodium hydroxide simply because the solute being an acid, you cannot titrate it against another acid. So you have to choose a base or an alkaline solution. But we are going to look at other cases where solutes are different, different from acids. So after getting, since you know the volume of sodium hydroxide, you can easily get the concentration of butane dioic acid in the aqueous layer. And after getting the aqueous layer, you have to look for the organic layer, which you get by subtraction. We shall look at the live examples of calculations. Then now, after that, you can easily get the partition coefficient, which we say that is the ratio of the constant ratio of molar concentration of the solute in a certain solvent, which has been mentioned first, water, to the concentration of that very solvent in another solvent, or rather the solute in another solvent. Nice one. Is that experiment clear?
It is clear.
Good. Okay. Let me go to another experiment. I will share this. Let me go to another experiment. B, determination of partition coefficient of iodine between water and tetrachloromethane. Determination of partition coefficient of iodine between water and tetrachloromethane. Still, that is the same procedures. We're going to follow the same procedures, but we are going to change the standard solution and the indicator, but the rest of the things are the same. So here, you get a known mass of iodine, and you add it a known volume of tetrachloromethane in a separating funnel to make a solution. Then you add a known volume of water to the mixture, and then you stopper the funnel. Okay. Now, what happens is that the mixture is going to be shaken and allowed to settle so that equilibrium is established at constant temperature. And then the layers are going to be separated, and then a fixed volume of aqueous solution is pipetted and titrated with the standard solution of sodium thiosulfate. We said that when we have iodine solution, or rather when we have iodine as our solute, we use standard sodium thiosulfate as our standard solution, and starch as our indicator. So that is where the trick is. So let me summarize these steps. Still, we shall say that a known mass of iodine is added to a known volume of tetrachloromethane in a separating funnel to make a solution. Step 2, a known volume of water is added to the mixture and the funnel stoppered. What next? The mixture is shaken. And then allowed to settle so that equilibrium is established at a constant temperature, at a constant temperature. Then, after equilibrium has been established, the layers are separated. And a fixed volume of the aqueous layer is pipetted and titrated with a standard solution, of sodium thiosulfate, using starch indicator. Meaning we shall have thiosulfate ions from sodium thiosulfate reacting with iodine, which has been dissolved there. We shall form tetrathionate ions, S4O6 2- plus 2 iodide ions. Now, the fact that you know the concentration of sodium thiosulfate and its volume, you can easily get the concentration of iodine in an aqueous layer. After getting the concentration of iodine in aqueous layer, you can get the concentration of iodine in organic layer by subtraction, and then you obtain your Kd. So we are going to say from the volume of standard sodium thiosulfate solution used, the concentration of iodine in aqueous layer is determined. The concentration of iodine in aqueous layer is determined. After determining the concentration of iodine in aqueous layer, then you can determine the concentration of iodine in organic layer by subtraction. Obtained or determined by subtraction. Now you've gotten the concentration of iodine in aqueous layer, and you've also gotten the concentration of iodine in organic layer. So what do? What we do is now to get the partition coefficient Kd. All right, so we shall say partition coefficient Kd is then obtained from the expression Kd is equals to concentration of iodine in water, because they said that determination of partition coefficient of iodine between water and tetrachloromethane. So you begin with water over the concentration of iodine in tetrachloromethane, CCl4. That is how we get the Kd. So we've looked at cases where we have a solute as an acid, that was butane dioic acid. And here we have considered where we have a solute as iodine. So let's consider an experiment where we have the solute as an alkali, because we say that if the solute is an alkali, then our standard solution must be an acid. Nice one. Are these two experiments well understood?
Yes, they are well understood.
Good. Anyway, from this we are going to another. This one I will not write all the steps, but instead guide you. You can merge the steps. The steps are the same, only that you change the indicator and the standard solution. So determination of Kd, or partition coefficient, of ammonia. This ammonia now is an alkali, between water and chloroform. Chloroform is what we call trichloromethane. So one can call it chloroform or trichloromethane. Now, having ammonia as our solute, we shall now use an acid as our standard solution. And we prefer using hydrochloric acid. And when you use hydrochloric acid, then the indicator should keep phenolphthalein indicator. So now here, still, an aqueous solution of ammonia of a known concentration is prepared, and a known volume of this solution is transferred into a separating funnel, because you cannot say that you have prepared a certain mass of ammonia. No. It is a solute, but in aqueous solution. So we shall prepare a known concentration of ammonia, then we transfer a volume of part of what we've prepared, a volume we're interested in into a separating funnel. Then we add a known volume of trichloromethane or chloroform into the solution, the separating funnel. Then you add water, of course, and you shake until equilibrium is established at constant temperature. Then you will separate the layers, and the fixed volume of organic layer now is pipetted and titrated against against hydrochloric acid using phenolphthalein indicator. Okay, so now our hydrochloric acid is going to react with ammonia. For this case, shall have ammonia solution reacting with the hydrochloric acid, and we shall form ammonium chloride. Ammonium chloride shall form ammonium chloride as our aqueous solution. Now, from the volume of the standard hydrochloric acid used, we can get the concentration of ammonia in the organic layer, because that is what we pipetted. Okay, we pipetted the organic layer, because after separating the two layers, a fixed volume of organic layer is pipetted and titrated against the standard solution of hydrochloric acid using phenolphthalein indicator. And now, having known the volume of the standard hydrochloric acid used, we can get the concentration of ammonia in the organic layer, which is determined, and the remaining concentration in the aqueous layer can be obtained by subtraction. But the partition coefficient still, the expression will keep Kd is equals to concentration of ammonia in water over concentration of ammonia in trichloromethane. The difference here is we have used the hydrochloric acid, phenolphthalein indicator, but on pipetting, we pipetted a known volume of an organic layer. So the aqueous layer is the one that we shall obtain by subtraction. Are we together?
Why did we this time pick from the organic layer?
Hey, you're asking why did we pick from the organic layer? There is no disease. There is no disease of you picking. There is no disease of you picking from the aqueous layer, but we are looking at the type of this reaction. You have ammonia, then an acid, ammonium chloride. Still, it has no harm. It has no harm. But let's pipette. Let's pipette the organic layer. But it has got no harm. Still, you can consider it like the way we have considered the other one. You can still pipette the aqueous layer, and then you obtain the organic layer by what? By subtraction. Do you understand that?
Yes.
We are going to do, now we have looked at what it is. Okay, we have looked at the experiments. Now let's look at how do we apply the knowledge we have already obtained. Let's see how we can apply this knowledge of what we have already obtained. Okay, let's look at how we can apply the knowledge of what we have already obtained. So we are going to do examples. And these examples we are going to do them basing on the experiments that we have carried out. In other words, there is a relationship between what we've carried out and then the examples we are going to do.